Log on, tune in, find out. Another good idea from Cambridge.
Continuation of the series on perverse sheaves and derived categories.
Okay, thank you. What I want to talk about today is the decomposition theorem, which is certainly one of the most well-known and important results on perverse sheaves. I'll state a version of it which is maybe reasonably familiar. I mean, perhaps many of you have seen this statement somewhere. So the setup is this. So if F is a proper morphism of varieties, and Y is smooth, and F is semi-small, and it's semi-small. It's some technical condition on the dimensions of fibers of F. I think I won't write down exactly what it is, but anyway, it's some inequality. Then the statement says that if you take the derived push forward of the constant sheaf on Y shifted by the dimension of Y, so you start with a constant sheaf on Y, and then we're going to take the derived push forward and wind up in the bounded derived category of sheaves on X. Then what you get is a direct, well, it's a semi-simple perverse sheaf. So it's a direct sum of simple perverse sheaves. Okay. So one thing that's a little bit mysterious about this is that the origins of this theorem are in the positive characteristic setting. So I'm going to leave this statement up here, but for most of the talk, I want to work in the following setting. So X is going to be a variety over the algebraic closure of a finite field, but defined over FQ. So all I mean is that we think of it as a variety over this field, but the defining equations have coefficients in this field. And so in particular, that means that you could think of the FQ points of this variety. So you get those from the Frobenius morphism, which is the map that raises all coordinates to their qth power. On the algebraic closure of FQ, when you raise things to the qth power, the points that are fixed by that map are exactly the points of the finite field. So X superscript F is going to mean the Frobenius fixed points. And that's exactly the points of this variety that are defined over FQ. So the FQ points of X. Okay, and then we're going to work with QL bar sheaves in the étale topology. So I'll say a few words about this, but most of the time in practice we can ignore how complicated this setup actually is. So the first problem, I mean, up until today I've mostly been talking about complex varieties with the classical topology. And whenever we want to talk about constructible sheaves and perverse sheaves and stuff in algebraic geometry, the first problem you have is that the Zariski topology has way too few open sets. So, for example, if you think of the complex one-dimensional complex space minus the origin, that has no non-trivial local systems in the Zariski topology. And somehow that's the wrong thing. That space really is supposed to have local systems that are not trivial. And so the étale topology is the way to fix this up. So I'll just make a few comments about this. So one is that the étale topology is not it's not a topology in the usual sense. So it's not an ordinary topology. It's instead something called a Grothendieck topology. But at any rate, there's some notion of open set in this topology, which is a little bit different from what you have in ordinary topologies. And then once you have a notion of open set, you can try to write down a definition of sheaf with respect to it. And then there's a second complication, which is that QL bar sheaf does not, I mean, even if you sort of know what the étale topology is, this doesn't mean a rule which assigns, I mean, normally a sheaf is an assignment of a vector space to each open set. So QL bar sheaf does not mean assignment of QL bar vector space to each étale open set. It's something much more complicated. It's an inverse system of sheaves where in each term in the inverse system you're assigning modules over z mod L to the n or something like that. So these are the finite groups whose inverse limit is exactly ZL. And then how do you replace ZL by QL? Well, there are various sort of technical things you need to do. But basically, you can usually ignore these complications. So in particular, when you take a stalk of a QL bar sheaf, well, you have to work a little bit to make sure you have the right definition of stalk, because the word sheaf itself has changed meaning a little bit. But once you set it all up, everything's OK, and a stalk of a QL bar sheaf really is just a QL bar vector space. Same for all the other things. So the same for, I guess, other usual sheaf operations. You have to be a little careful in the setup, but you know, intuition that you have for sheaf operations from topological spaces generally carries over. Okay. Okay. Oh yeah, and let me also mention, I guess this will be note 3. QL bar is isomorphic to the complex numbers sort of abstractly, but you certainly can't write down an isomorphism. And I guess this number 2 is the reason that we can't just talk about sheaves of complex vector spaces. If a QL bar sheaf was just an assignment of QL bar vector space, you could just replace that by C. And somehow instead this, the fact that you're working over an L-adic field is important to the technical details of the construction here. Oh, and I guess I should have mentioned somewhere along the way that that L is a prime not equal to the characteristic of the finite field that we're working over. Okay, but anyway, so once you have all this stuff set up, then the kinds of categories that we've been talking about in the past few days, you can write down definitions that are basically the same. So you can talk about the bounded derived category of sheaves with constructible cohomology. and you can talk about the perverse T structure on this category. I can't remember if I explicitly wrote down this notation before, but I'm going to write P of x for the abelian category for the heart of the perverse T structure. So that's the abelian category of perverse sheaves. So these are all defined as before. There's one caveat here, which is that, well, when we wrote down the definition of the perverse T structure on Tuesday, we had real dimensions appearing all over the place. So now we need to replace that by something, because there's no such thing as real dimension here. And fortunately, just about every place where you saw a real dimension, there was a 1/2 in front of it. In the algebraic setting, I mean, generally algebraic dimension, well, for a complex variety, certainly, algebraic dimension is twice real dimension. And so maybe by analogy or something, we're going to replace all the instances of 1/2 real dimension by algebraic dimension of a variety. Okay. So everywhere in the definition, just make that replacement. Okay. Okay. So now, if f is a QL bar sheaf on X, so I want this sheaf to also be defined over FQ. Then the Frobenius morphism induces, well, so the Frobenius is a morphism from X to X, and then the script F is a sheaf on X. So, well, you can pull it back along that morphism, and the Frobenius induces an isomorphism, which I'll denote phi, and it's an isomorphism between the original sheaf, script F, and its pullback by the Frobenius. And in particular, if you take a point, if you take an FQ point of the variety, so a point that's fixed by the Frobenius, then this isomorphism of sheaves gives you a, when you pull back along the Frobenius, of course, it doesn't change the stalks at points that the Frobenius fixes. So this isomorphism gives you an automorphism of stalks at points like this. So it gives you an automorphism, which I'll denote phi x of the stalk fx. Okay, and then the main idea for today, for the rest of my lecture actually is we're going to try and keep track of the eigenvalues of this automorphism and then extract information from those eigenvalues. Okay, so these are just some finite dimensional QL bar vector spaces, which are kind of like complex vector spaces. So, okay, so keep track of eigenvalues. And these eigenvalues, roughly correspond to the word weights. So I'm going to be a little more precise in defining the word weights. So okay, so yeah, I guess the sort of when I was listing topics on Monday, I said today's topic is going to be weights, purity, and decomposition. So we'll define weights and we'll define purity right now. Purity is the definition is really well. It's not really long, but it takes several steps to get there. There's sort of some lemma definitions. I don't know. We need some pre-definitions before we get to the main definition. And unfortunately, the earlier definitions also use variations on the word purity. So this is a little bit of a headache, but it's not actually so complicated in the end. And I think it's worth writing down what the definition actually is. So here's the first step. So F is still a sheaf. Later on, we're going to get to objects in the derived category. So F, a sheaf, is pointwise pure of weight. And then, unlike in every other talk this week, the letter W does not stand for an element of a Weil group or a reflection group or something. It's an integer. OK, so F is pointwise pure of weight W if for every FQ point of the variety, so for every Frobenius fixed point, the eigenvalues of that Frobenius automorphism, so all eigenvalues of phi x are algebraic numbers with absolute value q to the w over 2. OK, so this sentence is incomplete because the word absolute value doesn't quite make sense here. Absolute value is something you can take for a complex number, and QL bar is isomorphic to the complex numbers, but that isomorphism is certainly not unique, and you can't pick one. I mean, you can't even write one down, but this should be something that's true under any isomorphism. QL bar to C. And somehow, I mean, you don't have to think about all of QL bar. The fact that, I mean, to say it's an algebraic number, I mean, it's a algebraic over Q, which is, of course, a subfield of QL and of QL bar. So maybe you'll only need to sort of think about a piece of that isomorphism. So here, well, here's a small example. The naive constant sheaf. I'll say why I'm writing the word naive in a moment. QL bar, and then I'll write an underline under it to make it into a sheaf. The naive constant sheaf on X is pointwise pure of weight 0. But there's something you can do in this setting which doesn't have an analog in the topological setting, which is that once you have a sheaf, you can modify the action of the Frobenius on it. So you can modify its weights, and this operation is called Tate twist. So this is actually some kind of tensoring with a specific sheaf that the Frobenius acts on in a certain way. And then when you do that tensoring, you change all the eigenvalues in a certain way. And so you can take the constant sheaf and twist it by 1, and then you get a new sheaf which is pointwise pure of weight -2. I guess the general formula is that, well, maybe I'll just change it here. If you twist by n, you get a pointwise pure sheaf of weight negative 2n. This is still a local system. I mean, actually, maybe local system. Sometimes people don't really want to use the word local system in the étale setting, but instead refer to smooth sheaves instead, because local system. I mean, the idea of locally constant is not entirely appropriate, but anyway, it basically plays the role of local systems in the classical topology. So. Oh, right. Okay, yeah. You're absolutely right. Yeah. So. Okay. So. Yeah, I guess I need to go back here and say that power is so f to the n. The Frobenius, if you raise f to the nth power, that gives you the fq to the n points, and then that also gives you so I guess phi. Well, so that the nth power of the Frobenius gives you some corresponding automorphism on stalks at fq to the n points, and this should be. I guess I just need to add an nth power there, and then yeah. Yeah, okay. Yeah, I guess I shouldn't have used the letter N here then. I can just make it into an M. Okay. Okay, so then the next definition is that F is mixed if it has a finite filtration with pointwise pure subquotients. Okay, so this is still a statement about a single sheaf, and then typically you'd say mixed with weights less than or equal to W or something like that. If all the pure subquotients that you get have pointwise weight less than or equal to W. So now that we have these two definitions for sheaves, we can define a triangulated category dBmx, which is the full subcategory of dBcx. So this is already, remember, a full triangulated subcategory of dBx, where we're requiring all the cohomology sheaves to be constructible. And now we're going to add another condition. So this is the full subcategory consisting of objects whose cohomology sheaves are mixed. Okay. And then so this is a full triangulated subcategory. So again, just as with this category, that means that when you have a morphism of two objects in here, and you form the cone of that, the cone is again a mixed object. So that ends up in the same category, and this category is preserved by all the usual sheaf operations. And so for the rest of the hour, we're only going to work in this mixed category. I mean, it's I mean, I guess the point is that the objects that sort of arise naturally under any sort of reasonable construction are always going to be mixed. I mean, you can write down an object without any trouble which is not mixed, but those are not the ones that are useful for the kind of things that we want to study. Okay. So now here are some definitions for for complexes in the derived category. So a complex in dBmx is said to have weights less than or equal to W, and this definition is not what you might guess at first. The definition is that a complex has weights less than or equal to W if the nth, or let me use K instead. If the kth cohomology of F, so now that's an ordinary sheaf, so we have those definitions. So it's supposed to be mixed. Well, it's automatically mixed because we're in the dBm category with pointwise weights less than or equal to W plus K. So this is a different condition on each of the cohomology sheaves. And let me draw a little picture. I mentally think of shift in the derived category as moving things up and down. I mean, even though I often, I think of chain complexes always going vertically. So the vertical axis on this picture is cohomological degree. And then the horizontal axis is pointwise weights. And then if you pick an integer W there, then the collection of objects in the derived category which have weights less than or equal to W, it's not the category to the left of the vertical line here. It's the category to the left of this diagonal line of slope 1. So, yeah, so as you go up in cohomological degree, you're allowed bigger pointwise weights. So these are objects of weight less than or equal to W. And then there's a notation for this category. So this category is denoted D less than or equal to W. So D less than or equal to W is the category of complexes with this property. Okay. And then there's one more definition. I define less than, I have to define greater than, and that's also not what you think. Okay, so so F in dBm x has weights greater than or equal to W if its Verdier dual has weights less than or equal to minus W. Okay, so in general, this is not something that you can you can check by a condition on cohomology sheaves like you can for the less than condition. So let me make a couple of side remarks. One is that if X is smooth, then oh wait, I guess I need to define pure first. So F is and this category is denoted D greater than or equal to W. And then F is pure of weight W if it's in both the less than category and the greater than category. Okay. So here are some side remarks. If X is smooth, then Verde duality and Poincare duality work a lot better than if X is not smooth. And in this case, it turns out that a complex is pure of weight W if and only if all its cohomology sheaves are pointwise pure of weight W. The kth cohomology sheaf has to be pointwise pure of weight W. Constructible is not enough. No. Okay. Okay. So. Okay. Yeah. I guess. Okay. Yeah. So if X is smooth and all the HK are local systems. Then pure and pointwise pure are the same thing, but not in general. And then so this definition took forever, and maybe I'll say a little bit about where it comes from. This theory of weights was developed by Deligne in his proof of the Weil conjectures. And one bit of the Weil conjectures is the sort of following expectation. So for X smooth and projective, the expectation was that the Frobenius should act on the cohomology of X. So by this I mean sheaf cohomology. So this is the L-adic version of singular cohomology or something like that. So this is really the kth cohomology of derived global sections of the constant sheaf. So it should act on the kth cohomology with eigenvalues of absolute value q to the q to the k over 2. So the theory of weights in the derived category of constructible sheaves is sort of set up to sort of get at this kind of statement, and then the actual collection of statements that Deligne proved are statements about how various sheaf operations, what various sheaf operations do to weights. Okay. So this is let me call this well, I don't know. I was going to call it fact, but I don't think I'll write down all the formulas. So well, anyway, I'll call it a fact. What's in here is a description of the behavior of the sheaf of the usual sheaf operations. So sheaf Arham. There's derived tensor product, which I haven't mentioned so far. It has a little L over it instead of an R because tensor product is a right exact functor, so its derived functor is derived on the left side. Then there's derived push forward, pull back, and then there are the Schriek versions of push forward and pull back. On the weight categories, well, taking derived global sections is just an example of pushing forward to a point. So somehow that result comes out of this collection of statements. Okay. But then you can deduce some more things from this fact. So the next thing, which I'll call corollary 2, is that if F has weights less than or equal to W, and G has weights greater than or equal to W, and let me put a star here. I'm going to add an extra condition, and both are actually perverse sheaves. So they're not just arbitrary complexes, but they're actually perverse. Then Hom F G Hom of F with any shift of G vanishes for all positive numbers n. Well, maybe I'll make a comment on the proof of that. It actually turns out that if G actually obeys a stronger condition, so here we're imposing one inequality on the weights of F and sort of the opposite inequality on the weights of G. If G happens to be in D greater than or equal to W plus 1, so if its weights are strictly bigger than W, then this condition actually holds without any assumption like star. So this holds without star. If this condition fails, so if it's in greater than W but not in greater than or equal to W plus 1, you can try to do the same kind of computation. So the proof of this statement is a computation that comes out of this big fact due to Deligne. The second thing, if you try to do the same thing, you wind up with a calculation that reduces this Hom group down here to Hom is something kind of different, to a Hom group with a negative shift in it. And this negative shift, well, this doesn't actually have anything to do with perverse sheaves in particular. It's really just a statement about T structures. That Hom group right there vanishes as long as F and G are both in the heart of some T structure together. So this is from axiom 1 for a T structure. Okay. And then here's corollary 3 of this statement. A simple perverse sheaf is pure. I'll give you a fake proof of this. This is the kind of proof like, in calculus you sort of prove the chain rule by canceling differentials or something. This is going to be that kind of proof. It's nonsense, but it has some seed of an actual idea in there, which you can sort of fix up into a proof. And the fake proof is like this. So a simple perverse sheaf is something like, well, the way we've been naming them is ICSL. So let's suppose S is an open stratum. So if it's not, somehow you can reduce to the case where you're talking about an open stratum, and then let J be the inclusion of S into X. On Tuesday in the discussion section, I talked a little bit about the construction of the IC functor, and one way was with this functor, which is called J shriek star, which is sort of between J shriek and J star. Okay. Well, so part of fact one, which I didn't spell out, is that J shriek preserves D. Let me make sure I get this the right way around. J shriek preserves D less than or equal to W, and J star preserves D greater than or equal to W. Okay, so the word between, of course, doesn't really have a precise meaning, but somehow the intuition from this is supposed to be that J shriek star preserves both. So you start with a local system, which is pure, and then you apply the J shriek star functor, which preserves purity, and then you get a pure object, and that's that. Okay, so here's an actual theorem. Every pure perverse sheaf is semi-simple, and I mean, modulo all the facts and stuff that I wrote down without proof, we can actually do the proof of this theorem. And this is somehow half of the decomposition theorem. So here's the proof. So let F dot be a pure perverse sheaf. Okay. And then let K be the sub-perverse sheaf, which is the sum of all simple sub-perverse sheaves of F. So this is the maximal semi-simple sub-perverse sheaf. And remember that in the category of perverse sheaves, you have to be a little bit careful with words like sub-object. So this means that there's a morphism from K to X which is injective in the categorical sense. It doesn't mean anything about injective maps of sheaves and cohomology or anything like that. Okay, so now, well, just form the quotient of F by K. So let's form the short exact sequence. So K is a sub-perverse sheaf of F, and then form the quotient and call that G. And well, so what's a short exact sequence in the heart of a T structure? Well, that's the same as a distinguished triangle, where all three terms are in the heart of the T structure. But let's switch to regarding it as a distinguished triangle. So then there's this extra map here, which is the derived category version of the boundary homomorphism in the snake lemma. And now, well, we need one other fact, which is that subquotients of perverse sheaves respect weights. You can't get weights that you didn't already have. So in other words, since f is pure of some weight, k and g also have to be pure of that same weight. They can't have any bigger weights or smaller weights. So g and k are pure of the same weight as each other and as f. But then corollary 2, which I've erased, but whose comment on proof is still up there, corollary 2 says that this map has to be 0. It says that Hom between two things that are both pure. Well, it had inequalities in its statement, but certainly these satisfy those inequalities. And for the vanishing, when they actually have that weight, you needed them both to be perverse sheaves, and they are both perverse sheaves. This is 0, so that map is 0. And when the boundary map in a distinguished triangle is 0, that means that the distinguished triangle splits. So the distinguished triangle splits. So that means that f is the direct sum of k and g. But that's a contradiction. K was supposed to be the maximal semi-simple subobject of f. But, well, g is a perverse sheaf, and it has some simple subperverse sheaf. And so a simple subperverse sheaf of g is going to be a simple subperverse sheaf of f, which we forgot to include in k. So g contains a simple subobject not in k. Okay. Okay, here's another theorem, whose proof is quite similar to this purity theorem that we just proved. This theorem says that every perverse sheaf, not necessarily pure, admits a canonical finite filtration. So I'll write that something like FW contained in FW plus 1, FW minus 1. So I want to allow the subscript to be whatever integer, but the sequence stops after finitely many steps in both directions, such that the subquotients of this filtration, so FW mod FW minus 1, is pure of weight W. And then I didn't end up adding any exercises to my webpage for today, so this will be the exercise. So, okay. And then the last thing is the decomposition theorem. So maybe I'll just come over here and modify this a little bit. I'll change the C to a QL bar. I guess that's the only change I need to make. Okay, so then here's the proof of the decomposition theorem. Okay, so let me make a couple of observations first. So the first one is going to be that by fact one, the big theorem of Deligne on how sheaf operations affect weights. Well, one thing that's contained in fact one is that push forward along a proper map preserves both kinds of weight categories. So it preserves both d less than w and d greater than w. So it takes pure objects to pure objects. Okay. The second observation is that, well, the object that we're pushing forward here is the constant sheaf on y shifted down by the dimension of y. So QL bar y shifted by the dimension of y for y smooth is a perverse sheaf. Well, in fact, it's a pure perverse sheaf. So, well, it's pure because it's just a shift of the constant sheaf, and it's perverse. This you can check directly from the definition of the perverse T structure that I gave on Tuesday using Poincare duality. Actually, even more is true. This is, I mean, the semi-simplicity theorem that we proved says that, well, if this is a pure perverse sheaf, it has to be direct sum of simple ones, and in fact, it has to be a single one. So this is actually a pure simple perverse sheaf. And then the last observation is that well, there's one word in the statement of the decomposition theorem that we haven't used yet, which is semi-small. And then, well, semi-small is a dimension condition, and the definition of perverse is a dimension condition. So the semi-small condition implies that that RF star, that the derived push forward, takes perverse sheaves to perverse sheaves. Okay. So let's combine all this. So now RF star of QL bar y shifted by the dimension of y. Okay, so the thing we're pushing forward is a perverse sheaf by part B. And so the answer is a perverse sheaf by part C. And it's pure by part A. So this is a pure perverse sheaf on X. And then we proved that any pure perverse sheaf is semi-simple. So this is semi-simple. Okay, so I was going to say something about the Springer correspondence, but I don't know. Maybe I should save that for the afternoon or something. So, okay, so I'll stop there.
Right. Are there questions, remarks?
So I assume because you didn't state it that it's not true, but is d bigger than or equal to w, d less than or equal to w a T structure?
No, it's not a T structure. So one thing that you can check right away is that when you shift one of these weight categories, the index moves the wrong way. So these things are defined by conditions that are different on each cohomology sheaf. So if you shift everything down by 1, then you end up in d less than or equal to w plus 1. But for a T structure, d less than or equal to n shifted by 1 gives you d less than or equal to n minus 1. So that maybe is just a notational thing. But maybe the deeper question is, the most important axiom for a T structure is the existence of these distinguished triangles. So you can ask whether there exist distinguished triangles that sort of cut off parts of a mixed complex with cut off the part with weight less than or equal to w and the part with weight greater than or equal to w plus 1. And the answer is no, but you can sort of fix it. So this is something I learned about from the thesis of Sophie Morel. So she basically you can modify the definitions of these categories a little bit to impose conditions not on, so the definitions I wrote down were definitions on cohomology sheaves. But you could instead write down conditions on perverse cohomology. So the perverse T structure is a T structure, so you get cohomology functors that go from the derived category to the category of perverse sheaves. And then if you write down conditions using perverse cohomology instead of ordinary cohomology, then these are still not quite like an ordinary T structure, but you do get truncation functors. So maybe that is the answer to your question. Yeah, okay, go ahead.
So you started out at the very beginning with the varieties defined over C. Can you say a little about how to get back up to C?
I cannot say very much. This is something that I don't really understand very well. Yeah, so this is a little bit of a mystery to me. So yeah, I think I can't say anything useful about it. So maybe there are people who can.
I don't think that's true. I think it's f semi-small means the image of the constant sheaf is perverse, but it doesn't necessarily send perverse sheaves to perverse sheaves.
It certainly doesn't have to be just the constant sheaf, because if y is not smooth, you can take if y is not smooth, you can certainly take the IC sheaf of the open stratum here, and you do get a perverse sheaf down here.
I think it might be true for things supported on the open stratum. But
Things supported on the open stratum.
Yeah.
Oh, okay.
The simple counterexample is provided by the blow up of C2.
Oh, okay.
Semi-small. If you take the intersection cohomology complex on the exceptional fiber.
Okay. Well. Okay. So at any rate, so this is correct.
Further questions? Let's thank the speaker again.